too much talent. It's actually, in some sense, an issue in statistics and machine learning that there seem to be there are so many good ideas like competing on the same problem. But actually, I put these slides in here because I thought it would, again, be a local connection. Because this was actually a paper about how soccer teams with too much talent weren't doing so well. So I thought in Barcelona you could relate to that. And the new finding from sports suggests that there's a limit to the benefit top talents bring to a team. That news report was reporting on this paper. Team interdependence determines whether when more talent is too much or not enough. Can we get rid of this stupid here? And this is what they found. So they had a measure of, these were from soccer teams actually, the percent of the players who were top talent on the team and the team performance, and some measuring you can see it was going down, which indicates that you shouldn't get that last extra player, apparently. Now, in their paper, they compared this. I'll get to where the data came from in a moment, but this was their empirical finding. But in psychology, it's not enough to show that you're right. You also have to show that everybody who came before you was foolish. That's partly because if it's like, okay, everybody knew this already, that wouldn't be so interesting. So they gave people these two axes, but without the curve. And they said, draw what you think would happen if performance is a function of talent. And then they averaged people's responses. And this is what people thought. So people thought that teams with more talent would do better, and that there'd be some diminishing returns. But people didn't expect this. So this is what was new and special in this particular paper. Now let's just look at the data. The team performance on some scale, the top talent, so this is interesting, the mean percentage of top talent in the data was 7%, and the standard deviation was 16%. Now I want you to think about that for a second. If the mean is 7% and the standard deviation is 16%, then how much information are you going to be getting from here? Maybe not a lot. There's some. You don't have to be like George W. Chebyshev to know that you just can't have a lot of data here if the mean is 7 and the standard deviation is 16. So I'm a little suspicious. So let's look at the data. And here are the data. And they fit these curves. I think people are giving them a hard time about that quadratic, and so they fit these instead. And they triumphantly reported that the first slope is significant and positive, and the second slope is not significant. Now, the funny thing is this looks a lot like what those naive people thought of the diminishing returns, but it doesn't actually look like what they claim that they found. So this is an example. This is not really a big data problem. But this is an example of the kind of little data concerns that we have. We have fitting models to data, understanding patterns, and then saying are patterns real? And like, it's not correct to say that this is significant and this is not significant, and therefore the difference means something. That's an error. That's a mathematical error. But these are the kind of concerns that we still have to worry about. Quick lessons here, that you can plot the data and the model together. You shouldn't overinterpret statistical significance. And nonlinear models can be tricky. Interpreting a curvature parameter, it doesn't always mean what you think it means. And I think maybe the best introduction to my talk is the first talk this morning. Because obviously that was big data. It was, what was it, a zillion prices there. And yet, when you actually looked at the conclusions that were being made, they were sort of little data things, like Japan looks different from these other countries. That's like n equals 7, right? Or we see this go down and that went up. So we have the Argentina data, there's internal replication. So we actually have to spend a lot of time evaluating evidence. And when it comes to evaluating evidence, well, that's what I want to talk about for you all. So today, I'm going to start with a very simple example from my own work with little data, and then we'll talk about some big data examples and how these ideas apply. And you should feel free to interrupt, or we could talk later. I think I have about 15 more minutes allocated. But okay, so this happened a few years ago. I got this fax. I don't know if you know about these. We used to have these little machines in the office, and paper. It was very strange because no one would ever put paper into the machines, yet paper would come out of it. So I think maybe we would put in liquid wood pulp or something. Last week we had an election. Many residents believe, as I do, that the election was rigged. This was an election for a housing development in New York City, a public housing development that had a local board that was elected, with fixed percentages being assigned to each and every candidate, making it impossible to participate. And there were a list of candidates. I changed the names, but there were a list of about 30 candidates, and they had the number of votes at different points. They had like election monitors. These are like hyper-political people, so they had to monitor, and they had their percentages, and these percentages seemed bizarrely constant. So there was a suggestion that they sort of knew ahead of time, almost like the Argentine, Department of Statistics or something, and that they knew what they wanted to get and were getting it. So I got this, and I was very excited because I was already picturing myself in the newspaper that I had saved the day, the statistician hero. So of course I helped them. So here were the data, and here you can plot. Now I listed the candidates in reverse order of the percentage of the vote that they received. Now, careful reader might notice that this percentage adds up to more than 100%, but that's because you're allowed to vote for up to 6 people in the election. And it looks very stable. Each of these lines they're actually based on 6 dots that are connected, or 7 dots, but it's so 6, but it's so stable it looks like straight lines. On the other hand, maybe it should be stable, right? Because after all, the percentage of the vote you received here is mostly from this, right? They're not independent data points, they're accumulations. So we can replot sorry, I don't have all. We calculated these not as accumulations, but as independent data points. Then for each candidate, I computed the standard deviation of the vote share of the person in the different segments of the election, and compared it to the theoretical standard deviation that you would get if people were just coming in completely at random, like the square root of p times 1 minus p over n. And here we have the results. Each circle represents candidate. There are 27 candidates. On the x-axis, I have the total number of votes. On the y-axis, I have the standard deviation of their vote proportions. The open circles are the data. The solid circles are the expected data based on if people were completely voting at random. And the hypothesis was that, or the claim was that the data were not variable enough. So if that were true, the open circles should be lower than the solid circles. And that's not what we see. So I would say the data seem completely consistent with just votes coming in at random. No evidence that anything is rigged at all. I could have done a chi-squared test, but I didn't really want to do that because you might argue they'd be doing some things with some candidates rather than others. So I wanted to see all the data. Okay, so this is just a little data thing, just to remind you of the kind of questions that come up. We have a pattern. Is it real? What does it mean? So we compare to some standard of randomness. The vote tallies are consistent with random data. It's no surprise if you think about it. When we do surveys of 1,000 people, traditionally the polls are accurate to within 2 percentage points. If they're off by more than 2 percentage points, we get worried and we say, what went wrong with the polls? So given that they were counting votes every 1,000 votes, it makes sense that they would look very stable. But perhaps it's just a lack of intuition about randomness that people have. Okay, now here's some big data. This was published here. 61 million person experiment. They put messages on Facebook reminding people it was election day and telling them to vote. And they found that the people who were getting this message, that among those people, voter turnout increased by 0.3 of a percentage point, which is plausible. It's something they did exactly on election day, so you can remind people. And they also found a social effect, meaning they looked at the spouses and roommates of the people who were sent the message, and their voter turnout went up too. It's like something like this amount. I should have maybe thrown a few more zeros in to emphasize the size. Now, I think at this point when people see these things, the statement is, well, they got it published, so the statement was it's statistically significant and it's social networks, so it's exciting. So this is a few years ago, back when social networks were considered exciting. But I think you expect me at this point to say it's statistically significant but not practically significant. I could say that, but I'm going to say it slightly differently. What I want to say is that it could be that you send this message in 2012 and it has a small effect of people talking their spouses into voting. It could be that if you sent this message in another year, it might piss people off, and then their spouses might be less likely to vote. That effects are variable. So my issue with these kinds of numbers is not that they're so small, as much as that I have no reason to believe that they're going to be stable. Right? And that relates to the idea that you need an external standard. And the external standard is not what I call practical significance, but rather some stability, reproducibility, replicability. So in the talk this morning, what you saw were change. You noticed that you weren't getting like, here's this change, the difference between Argentina, measured, the inflation measured one way and the other, and this difference is statistically significant because it's more than 2 standard errors. So that's not what you were getting. What you were seeing was that the changes were large relative to what was happening from month to month and year to year. So the key was that there was a natural scale of variation. And that's relevant here. So that's what's missing in this study in some sense. It's like, what does this mean? What is this being compared to? And having 61 million persons doesn't save you from that, right? The little data question of why should we care about this, I hate to even say why should we care, because that sounds like too soft a question. Like that's like for the English majors, English isn't the right thing. That's for the humanities majors, the poetry majors to study. But that's not what I'm saying. I'm saying this is a quantitative, well, what are you going to do with this? Are you going to say it's going to appear next year? Well, I don't see why I should think this is going to appear next year, because it happened once. Okay, here is another example. Genetics, that's big data. We expected reported anxiety to be significantly higher. These were one of these genetic scores. So let me just go back. I don't want you to read this, even though I put it up here. The interaction terms are both negatives. The interaction term with genetic risk score is significant at the p less than 0.05 level, and that with genetic risk score is significant at the p less than 0.10 level. I didn't know you were allowed to say that, but I guess in genetics you can do that. But here's my point. Big data genetics, those little things that look like spiral staircases, protein folding, biology. For decades now, I've gone to talks in statistics departments where someone comes and they're talking about genetics, and they always spend the first 10 minutes of their talk showing that curly thing and this curly thing, and they say, the fundamental dogma of statistical genetics is, it's like, I hate that. It's so mystifying. Like, do you see that? Like when someone talks about econ, do they say, we're first going to tell you about supply and demand? No, they just get right to it. But no, genetics is like, oh, this is, okay. So you have to watch out. Or, for people who do that, right? We're working on online auctions, so, okay, this is very complicated. So no, it's big data, that's fine, okay? The point is, when it's all at the end, what are they doing? P less than 0.05, P less than 0.1. So these issues are still there, okay? They still have to communicate in this language. How could that be? If the data are so big, everything should be statistically significant, right? Like, well, not really, because there's a lot of genes, but maybe this study only had 14 people, right? Now, they did discover the genetic secret to a happy life. So I was interested in learning about this. I felt like it's too late for me in both dimensions, I suppose, but maybe for future generations something could be done. So I looked this one up. They identified a happiness gene. And I was curious, so I looked in the research article. Having one or two alleles, that's another thing, by the way. If you ever want people to think you're sophisticated, use the word allele in your talk. And you don't have to define it. You can just say, like, I got these alleles running around, and it raises the average. So I saw this, and I was like, something funny about this. Like, 17 is twice 8.5. Well, it's not exactly, but there's round off. I just was suspicious. Like, one allele is this and two is that. It's like 2 is too close to twice of 1. I don't believe it. I think it's one number, and then somehow they made a mistake so they don't round up. So let's see, I looked up in the table. So they had 46% of people had 2 copies describe themselves as satisfied, and 41 very satisfied. The corresponding, if you start looking at this, it's not 8.5 or 17, it's 4 percentage points, not 17%. Well, and 4 percentage points is not 17% of 44 either. It's just, so this happens a lot, okay, because what happens, like people say, this is what we saw, but it's not really what they saw. It's like after they ran the regression. People don't tell you exactly what they did. Anyone who's ever been in a supervisory position will know that if you ask people to tell you what did you do, they find it very difficult to tell you that. But again, this is going to be, these things are going to be in the border of statistical significance. Everything's on the border of statistical significance. Everything is 2.1 standard errors away from 0. So you know why that is? Because if it was less than 2 standard errors away from 0, it wouldn't be published. And if it was 4 standard errors away from 0, then you'd break up the data into smaller pieces. And then, I mean, it's the same reason they don't give you a 3-kilogram steak, because they've already realized that you're not going to eat it all. So they're going to divide it up into smaller pieces of steak for everybody. So we're sort of always on this uncomfortable border of not knowing whether to believe anything, even though it's big data. It's sort of horrible, but the way it is. This is another big data kind of thing. There's been a lot of surveys on life satisfaction or happiness. Their happiness is slightly different from life satisfaction. Watching TV makes you happy, but it doesn't give you satisfaction. So things are measured in different ways. But there's this finding, which you might have seen, that people my age are not happy. And this makes me happy, of course, because things are... But everyone accepts this. It's very easy if you're young, lots of job opportunities, so forth. That was intended to be a joke when to speak more slowly for this audience. But this seems wrong. This is it's just not, old people should not be happy. I mean, this is bothersome to people. So there's been a lot of explanations of this stylized fact. One story is that by then your kids have grown up and you've resigned yourself to what they've become, whatever it is, so you're all right. But it's much debated. Here are some data. This is probability of depression. And as you can see, this is pretty amazing because a little bit later you're going to have a negative probability. I have a funny story, but this is big data too. In the social science world, this is big. Now, because in the old days, you wouldn't even have survey data you could plot by individual year of age. I mean, we would this is very high resolution. Now, the funny thing about this was there was a paper, and they had a regression of the depression on age, and there's a quadratic term. The quadratic term was negative and statistical significant, and I was like, I know about that trick. It's negative and statistical. It's a crude quadratic regression. Remember the example from the beginning of today? I don't believe that. I want to see the data, and the guy was turn to appendix of our paper. We have the data. And I've never seen anything this quadratic in my life. This is the most quadratic thing I've seen since Galileo played cricket. It's incredible. Now you can start to actually consider issues in all seriousness, maybe some of these depressed people are no longer alive for other reasons. It's horrible, because now you're laughing and it wasn't a joke, but it sounds certain topics are hard to talk about seriously. But anyway, this was that. But here's another, I thought I like this example, so I wanted my students to be able to do it directly, so they could download data from the General Social Survey in the US, which has a happiness question since 1972, and you can plot this versus age. It looks similar to all the other graphs, so if you look carefully, you'll see that now the youngest and the oldest are the least happy. So in fact, this is what's called a fragile finding, that the age happiness data appears in some, pattern appears in some data and not others. There's a lot of debate about to what extent it's actually due to survey non-response. And the reason why I spent 10 minutes talking about this example was because the way we often proceed in social science is we discover a stylized fact and then we try to explain it, understand it, but it's not always clear that the fact is true. We can be trying to explain things that are actually artifacts of our data. And again, that's why I'm really glad I didn't speak first today, because I get to say this again. I like both this morning's talks. So the second talk, just at the theoretical level of saying, don't just accept what people have done before. Like, think about problems in a new way. I think that's sort of very important, sort of mathematically. And then the first talk, all the details about looking at your data, what to not believe. I love that you had certain data patterns that you didn't even believe yourself. I think that's important. So we have to be aware of that data quality issue and how to conceptualize it. Okay, so I have another example with a slightly more specific point. This is not really big data, but it's a very interesting little data point. This was from a columnist in the New York Times a couple of years ago. He wrote that people at the extremes, at the political extremes, are more happy than political moderates. None, it seems, are as happier than the Tea Partiers. You've heard about them in other countries. They tell you about, that's like how to put your kids to sleep. The Tea Party will come and get you. So this was sort of odd, because who would think that people at the extremes are happier? Like, it seems like if you're happier, you'd be more content and you'd be in the middle. Right? So here are the data. 2009, 2010 is when the Tea Party became prominent. This was survey responses. People categorize themselves as being in the extremely liberal or far left in the US context, or extremely conservative, which is far right in the US context. They were very happy, pretty happy, or not too happy. And it was actually the very conservatives who were not too happy. So this is not what the New York Times columnist wrote. The data actually fit our preconceptions. The sample size is reasonably large that I think I can trust this to some extent. So how did he think that? Well, here's another graph I'm going to show you. This is the same graph, but the data go all the way back to 1972, which is what happens if you pull out data from the General Social Survey on the computer. This is not scraping. This is like you Google GSS and they'll create graphs for you. Here, you see the very conservatives were more likely to be very happy. So over the period of 40 years, more conservatives are more likely to be happy. But in the particular Tea Party period, that was different. Now, this raises a very important general issue, which is how much do we pool? So in social science and econ, it's common for people to take data from 40 years and put them all together and do some sort of fixed effects regression to control for things. But then you can get problems like this. Things are not necessarily stable over 40 years. So, but how does that relate to the larger point of this talk is when we disaggregate, which is what we should be doing, then we get noisier results. Then we maybe need to do some sort of regularization. So one of the reasons why at the technical level, I'm not going to talk much about my technical work, but at the technical level, I spend a lot of time trying to get regularized estimates, more stable estimates, using prior information, using temporal stability or spatial stability to get more precise estimates. And a lot of people say, well, why do you need to do all this work to get more precise estimates? Why regularize? Why not just get more data? Data are cheap. Well, the trouble with getting more data is you're in a situation like this. So we need to disaggregate. We need to break up that steak into little pieces, not just because we can't eat all that steak at once, but because those steaks different. I mean, perhaps I'm pushing this analogy too far, but perhaps these different pieces of the animal are serving different functions, and I'm learning different things. Okay, so these two graphs, in some sense, motivate a lot of my technical work. Is that there's a temptation for people to say, I want an unbiased estimate. I don't want to regularize. I just want to do something simple. But how do they do that? How do they get to something simple? They get to it by pooling their data. So if you're not willing to pool your data because you want local estimates, then you need to respect that in your inference. Here's an example. This is attitudes towards abortion. So survey respondents were asked, given a 4-point question, a 1 to 4 scale. So a 1 means you oppose abortion under all circumstances. A 4 means abortion should be legal, all circumstances. And then we took the average responses among people who characterize themselves as Democrats, Independents, or Republicans. This is just an old survey kicking around. I mean, it's not, obviously I didn't do this survey myself. It's easy to get these data. We see a pattern, political polarization, since 1992. Well-known phenomenon in American politics. It's sort of complicated. The political parties polarized back here, but it took another 10 years or so, or 20 years for the voters to polarize by party identification as well. The Republican Party has had this idea for a while that they could maybe get more votes of Hispanics, Latinos, by emphasizing abortion, because Latinos in the United States are more conservative on abortion rights, but of course they're more likely to vote for Democrats. And will this work? So I'm going to show you some data. This graph is showing you the difference in attitude among percent pro-life. So what I'm showing you here is looking at self-declared Republicans compared to self-declared Democrats, the difference in abortion attitudes. So until about 1990, there was essentially no difference between the two parties. But since 1990, there is a big difference. Now, this second graph is the exact same thing, except I did logistic regression. Now, why did I do logistic regression instead of comparing? They're almost the same. The reason is that I'm going to do more modeling with the data. And there's only so much I can do by simply taking differences. Because if I slice the differences smaller and smaller, they become too noisy. Logistic regression, I can add coefficients and regularize, which is what I did. I won't give you detail. This is everybody. Now I'm going to show you by ethnic group. So this one's pretty stunning, actually. So are you ready to be stunned? Okay. It's not like, of course, now that I say this, it'll be less stunning. And now you're like getting ready to say, I won't be stunned, you know. Yeah, okay. So, yeah. Yes, essentially no difference among blacks and Hispanics, these lower income minority groups. The difference in abortion attitudes has been almost entirely among whites, and while others, it's a very small percentage of the US population. Political polarization on abortion is not happening among Hispanics, which might suggest that the strategy of appealing in this way isn't going to work. The raw data look much more noisy than this, but having fit the regularized regression, this is what we get. You can break things up further, which among whites, it's actually the higher income and higher educated people who are more polarized in abortion, which makes a lot of sense to me as a political scientist, but sometimes surprises people, because a lot of people think that like voting on abortion is like a low-class kind of thing to do, but actually, no, it's a very high-class white kind of thing. Again, we learn by breaking things up, and this is going to come up with any big data problem also. I have another story for you. It's sort of like the billion prices, except our data were just in hundreds of thousands. It's a survey we did on Microsoft Xbox. So it's sort of convenient to do a survey on the Microsoft Xbox because you can survey people in their living rooms without actually having to go into their living rooms. People could just play the game, and they got to vote. This was in the 2012 presidential election. And you got to play this Xbox game, and then here are the results. Sort of hard to see this, but the blue line is support for Obama, and the red line is support for Romney. This was the last month and a half of the election campaign. So as you can see, the two candidates were roughly tied. Then Romney pulled into the lead here, stayed above 50%. As you can see, Romney won the election. And that explains a lot of things. As you know, in the US, the economy has been improving, which makes sense given that Romney was running the country. We have national health care, just like Romney was promising. Of course, the army is like, you know, they're shooting people with drones all over the place, but what can you expect with a Republican president? So that's the way it is. No, for those who've been paying attention to politics, that's not actually correct. Romney did not win the election. And it's almost as if like people who play the Microsoft Xbox are not a representative sample of American voters. I mean, almost as if. Now, in your Billion Prices project, I heard that you did a lot of curation to make sure that your prices were sort of representative. So you did not have, like, your billion did not have 500 million of the price of a certain item, right? You mixed it up. Here we have survey respondents. We have everyone who's on the Microsoft Xbox who's willing to pay. So they're not representative. We need to do some adjustment of the data. I will skip this and go to the adjustment. So we post-stratified. So we know, we asked people their age and their sex and their education and what state they lived in and their ethnicity, and the Microsoft Xbox had too many young men and not enough old women, and you do all this. So we used rather than curating our sample, we adjusted our sample. So we used it to estimate the proportion of Obama and Romney support among every type of person, and then put those types of people together. We put the puzzle back together and estimated at the level of the whole country. And now we have Obama being ahead, and then there's a drop here, and then eventually Obama wins. This looks very much like, again, this is echoing the first talk today, because this looks very much like what you get from something like pollster.com, which is an aggregation of national polls. But the difference is sort of amazing. First, this is just something that Microsoft did, was sort of close to free. I mean, really the only cost, the costs were very low. It was opt-in surveys. But second, each data point, each day is independent. It represents not new respondents, because people, as I'll get back to, people were able to respond to the survey in more than one day. I think the median number of responses was, or the mean number of responses was 3 or 4 during the period, so you could go back and play it again. But each dot is a new set of survey responses. They're not moving averages, they just look smooth because things typically are smooth. So again, it's a lot like that earlier example. We do see a big drop on October 3rd. This was, Obama was ahead, and then Romney became ahead. There's a big slide. And what happened then, there was a presidential debate. And those of you who were in the United States at the time might remember that during this debate, Romney, as his smile indicated, did very well and looked very competent. Obama looked like very confused during this debate. And afterwards, the political pundits wrote, Mr. Romney has not only improved his standing, but taken voters away from Mr. Obama's column. And Karl Rove said Mr. Romney's bounce is significant. I put both of these because this guy's on the left and this guy's on the right, but they both said that. I think they're both wrong. And the reason why I say this is that we went back and took our data and adjusted by 2 more things. What political party you said you were, the respondents said they were, and how they said they voted in the previous presidential election. Having done that, the light line is what I showed you before, adjusting just for demographics. The dark line is adjusting also for partisanship. We see that about 2/3 of the variation goes away. And we call this the dejected Democrats and resurgent Republicans phenomenon. It goes like this. Up to this point, the light line is higher than the dark line, which means that Democrats are more likely to respond to the survey. And you know, Democrats in general are more likely to respond to surveys, people find. But it makes sense. Obama was doing very well. It just like seemed like a fun game to play if you're a Democrat. Let's respond to the survey. Then after this debate, more Republicans are responding, which makes a certain amount of sense. Because, like, do you want to play this game, vote in the election? If you're a Republican, yeah, let's see how Romney's doing. This will be fun, right? I want to check this out. If you're a Democrat, like, no, I don't want to do that. It's not so much fun. This is stupid. You know? So differential non-response is causing most of this problem, which actually sort of resolves certain mysteries in political polling. Often we see these large swings that, like during presidential nominating conventions, it's not clear why they should be occurring, but it could be having to do with motivating people to respond to the survey. And then we confirm this pattern in other ways. How much more time do I have? Like 2 minutes or 15 minutes? Okay, okay. So in statistics, we have this term, the blessing of dimensionality, which is that we can learn by asking a lot of questions at once. So in particular, like in this example, we didn't try to look at the statistical significance of a certain drop. What we did is we studied the entire time series. And again, you saw this in both talks this morning. Both talks this morning had this flavor that they're saying these are problems where people sometimes focus on individual things, but we're looking at the big picture. And I want to do that too. So what's the alternative of asking many questions at once? Well, you know, sometimes people are searching for that statistical significant p-value, or they're fishing for it. You get it, like they're, yeah. Okay, here's an example. This is a real, not working? Why is this not working, huh? Oh, no, it's stuck. Yeah, thanks, thanks. Okay. Okay, this was a paper. They found that women in certain time of the month were 20 percentage points more likely to support Barack Obama for president. Now, you know, there's some theory behind it, because Barack Obama is sort of like the girly candidate, and during that time of the month, the women are more female, and so they're, you know, more responding to that appeal. Actually, that's not quite what they found. What they found was an interaction between single women and married women. It was actually not married, it was whether they were partnered or not. Okay, so there's a little bit of this fishing going on. That there's not actually a main effect, but they searched for enough interactions, and they found one consistent with their theory. They had a very broad theory that was consistent with anything, basically. It was theory was sort of like Freudian psychiatry, or you know, neoclassical economics. You know, it was a broad theory that could encompass anything. It's a good thing for a theory. This is ridiculous because I already showed you that actually we have surveys, like almost nobody, less than 2% of the people actually changed their views during that last campaign in our survey, and yet they're finding 20% swings. But this is what's going to happen. This is sort of, and of course, this can happen with big data too, right? Which is that you have some data set, and you're looking for something, okay? And they made a big deal about this, like, okay, this is a stylized fact. It's not real. It's not correct. It's just something that was true for a particular sample, just from randomness. And what's sort of important about these studies really is not so much that they're wrong, but that they could never have a chance of being correct. Because any changes, swings in public opinion, or if they're less than 2 percentage points, well, you're never going to be able to find it in these studies where you're comparing different groups of people. You would need such a huge sample to determine. Remember, I told you earlier, like 2 percentage points, you could learn about that from a sample of 1,000 people. I think this study had like 100 people in it. It's impossible to, like, talk about low power. Like, you'd need 1,000. I don't even think it's 2%, but like, even if it were there's no chance. But I think the usual way that research is published and publicized, people don't realize this. Because there's this expression you learn called statistical power, which is like, what's the probability that you'll get a statistically significant result? That's based on the idea that science is a kind of game where if you get statistical significance, you have a win. So if you do a low-power study, like put 100 people in a study where you'd really need 10,000 to discover anything, people would say, oh, this may be low power, but that's okay, because then I'll probably lose. But this is a game where if you win, you lose, right? Because they won this, they got the big prize of being published, but they lost in the sense that they wasted their time and they weren't doing science. Now I'm hoping, I've heard that some of you are from the business world, and I'm hoping in the business world that the motivations are a little bit different. You're not trying to get published, but the statistical methods are still out there. So if you take this kind of approach as a paradigm, then you're going to be having problems, no matter how big your data are. Here was, I have another example. This, I wonder if I should skip this, and this is a good example, but maybe I should skip it. I'm going to give a lot of these examples we have are like silly studies in psychology. Maybe we don't need to talk about that anymore. I'll talk about something serious. I mean, this is not a joke. This is something serious, okay? This was a study of early childhood stimulation. So they went to Jamaica, these researchers, and they took 133 kids, and half of them got the intervention consisted of 1 hour weekly visits from community health workers over a 2-year period. This was done for 4-year-olds. So half of the 4-year-olds and their mothers got this intervention, and half of them didn't. Then they followed this study up for 20 years. The kids for 20 years, and then they recorded their incomes and their earnings, right? And they found that the kids who had the intervention group had 42% higher earnings than the non-intervention group. So that was very striking. I mean, this is a lot. Now, was this 42% statistically significant? Does anyone have any idea? The answer is yes, because otherwise they wouldn't have put it here. Because everybody knows you're not allowed to just put results on that aren't statistically significant. That's cheating. So yes, it was statistically significant. They had some multiple comparisons issues. There were actually not just 2 interventions, there were 4 interventions. And they had some data issues. Like a lot of the kids left Jamaica, so there's a question of how do you deal with that. Now actually, in this case, they kept them in. The ones who got the intervention were more likely to leave the country, and they also tended to have higher incomes. But anyway, this was their result. Now, I don't believe this 42% because, well, you know, it's statistically significant, so maybe it's like 42% plus or minus 20%, something like that, right? But like, it couldn't have been much less than 42% or it wouldn't have been statistically significant, right? So there's the statistical significance filter, which is because it has to be significant, it has to be large. So there's a bias. Anything that's published or reported is going to be biased large. There was some discussion, not of this, but of another study. So social critic Charles Murray wrote, to me, the experience of early childhood intervention programs follows the familiar discouraging pattern. Small-scale experimental efforts staffed by highly motivated people show effects when they are subject to well-designed large-scale replications. Does this ever happen in the business world? Probably not, right? I can't imagine. I'm being ironic here. I think this happens in the business world too, that someone has a great idea and you could even do a little study and then it doesn't repeat. Now what if you had a great idea and instead of doing a little study with 111 people, you did a big data analysis? Maybe it still might not replicate, right? Because what's not replicating is not what's happening in your zillion data points. What's not replicating is the natural variation from group to group, month to month, person to person, and so forth. Now, one of the people involved in the study defended it. I won't unpack this except to say I don't really find this defense convincing because I don't think he's really addressing the statistical concerns, which is that there's high variability. And basically, if you think about this, I'm not trying to pick on these people, but you do a study that like took 20 years of your life, 25 years of your life, and it's on something as important as helping poor kids, don't you think you're going to find something statistically significant? I mean, what kind of ogre would you be to? I mean, like, what if they had found a negative result? Then they could have unpacked it and said, well, some of them are moving to another country, so we have to correct for that, whatever it is. So you know, they sort of have a moral obligation to find statistical significance, and so they're going to do it. They'd be heartless people if they wouldn't, right? And then they're going to defend what they did. So I think this is very important. These issues. Okay. So in summary, I think that description is just so important. Measurement is important. What you're measuring matters, right? Because of course your conclusions are only as good as your measurements. Variation, effect size and variations, it's not just about discovering something or finding a pattern, but like if you find something, break it up, especially if you have big data, you have no excuse not to, right? So get your estimate and do it separately for each year or for each country or each sector of your industry, and then make the graph, okay? And if you're showing the positive effect in every one of 50, you know, in almost all of 15 different sectors, month after month after month, then I'll believe you, right? If you say I pulled 2 billion data points in and I have one number, I have no sense of variation to compare to. And that the variation is a little data idea that you can use. And that's the thing, the bigger your data, the more you can use this. The easier it is to just break it up and estimate different types of people, different groups. And finally, Bayesian modeling, which I didn't get into except like by implication. So in our Xbox study and in similar things, we adjusted to match the sample to the population. Otherwise, it would have been useless. And when you're doing that kind of adjustment, you'd like to adjust for large numbers of factors. When you do that, your models can become noisy, and then you want to use Bayesian or regularization methods that will give you more reasonable, plausible adjustments. And in many settings, of course, we really do have prior information, and we want to use that prior information. Like you don't, in statistics, there's this thing, until recently we're always embarrassed to use prior information, but you know, you're not going to go to heaven because you didn't use prior information. If you have, suppose you have two statisticians working for your company, and one is brilliant and never uses prior information, and the other is an idiot, but he happens to have access to priors and use them, then that idiot might do better because, so you want to make use of that. So I hope this will be sort of relevant in you thinking about your big data work. Thank you.
Yeah, you talk about psychology and political sciences. I want to talk about physics. Because then when you think about big data and the generation of big data, the LHC produces more data than all the internet together in many ways. So, and there you have searching for the Higgs boson, for instance. You say you're looking for pins all over the place. These guys have 2 detectors, and they have lots and lots and lots of data, and they were looking for a T larger than 5 because in physics this is a discovery. More than 5 standard deviations away is a discovery. 2 is just a indication. 3 is a strong indication. They have 2. One was given 2.5, the other was given 3.2. So they say, okay, instead of separating them, let's pool them together. You get 5, and here it is the boson, the Higgs boson. So you have exactly the same problems when you search in other sciences, not only the social sciences.
Physics is a little different, I guess, because it's a very small signal they're trying to detect, right? I mean, traditionally in physics, you would isolate the effect. You'd build a lab equipment. You know, if you wanted to test a certain subtle effect, you'd build a lab equipment that would isolate it. But obviously, in like particle physics, you can't do that. So that becomes much more of a challenge. But yeah.
I have a question related to the prediction you were talking about. What's your opinion about using exploratory data analysis in combination with the confirmation phases that we are really used to. How do you suggest to integrate or perhaps automate exploratory data analysis in this process?
Well, in a sense, like everything I do is exploratory. So sometimes this comes up, people will say I'll do exploration and then I'll use that to design a new study. And that's okay, but then I think if you want to, if you design a new study, I think again you want to use prior information in the design. Like it would be a mistake to do an exploratory analysis and then say, well, whatever is significant, I'm going to follow it up with a new study. Because then, like, what if something wasn't significant, but it's still important? You didn't get a chance to see it, right? So I think, I don't know that I would, so to me, there's not such a clear separation of exploration and confirmation. They sort of go together. I'm just trying to learn. Yeah. Yes.
So I think very much what you said, you have to make pictures and then this education. So in economics at least, most people who use empirical data just show tables with stuff. And if I tell them about make pictures, they say, but there are so many dimensions, I cannot make pictures. So where does it come with people?
I think that we need a better integration of theory and practice, which again relates a bit to the second talk this morning, that I think often that we have, like, often theory is considered to be sort of so distinct and people don't really think about how it would apply. So in particular, to me, I think of graphics as being model checking, in Bayesian term, posterior predictive check. So I think that classically, like, I would like to sort of not, I think currently the way it is people like in statistics or in econometrics will graph the data, like they'll say, well, I'm going to graph the data in order to decide how to specify my model. But once I specify it, I never look back, right? You just start making tables. But there's, I think if you recognize that the models have a potential for improvement, then you want to see where the models fit or don't fit. So graphing the data in order to decide how to fit the model is much more effective if you can graph the residuals from the model or make graphs relative, the data relative to the model. So to me, I think that's the answer. I mean, certainly it's communication. So you should graph, you should communicate. But like if you go back to the example at the very beginning of my talk, people, they made the graph and they couldn't interpret their own graph because they had already made this story, right? But it was helpful to me that they made this graph. So, maybe I think that would be, like if you accept it. I think in econometrics there's this attitude that models should be robust, so it shouldn't matter if your model is wrong. But I think that robustness is one of these things, like it's good to be robust, but you'd also like to improve your model. I don't know.
Any other questions? All right, the same amplifier.